welcome to this evening's workshop. We decided to run this series called Nail Your Technical Interview, which Parker came up with, by the way, which I think is great. And a great series of events to have here at Galvanize. At Galvanize, of course, I think you know we have a web development immersive program. We teach people to be web developers here. And so as part of the programming, of course, we try to teach people to nail their technical interviews. We give them a lot of different careers curriculum throughout the program, a lot of computer science curriculum throughout the program, so that they're most successful in finding jobs afterward. I'm Andrew Fitch. I work here at Galvanize as the evangelist, and that means that I talk about Galvanize. So that's what I'm doing here right now, as you may have guessed. But I also, in doing and talking about Galvanize, I set up a whole lot of different events. So this is just one of many that we have in the space, from hackathons to workshops to tech talks to all sorts of different types of events, as well as conference sponsorship and everything too. So if you're at conferences and hackathons around town, you may also see me there. A little bit, I guess, about the bigger picture of Galvanize. We call ourselves the technical learning community, or learning community for technology, either way. And that means that we're made up of a whole bunch of different sort of learning opportunities here in the space, one of which is these events. Great. We offer like 3 events to bring people into the space and to educate the overall community. We also have, I mentioned, the web development immersive program that's 6 months long. It happens not in these classrooms, but in a similar classroom on the 4th floor with pairing stations just outside of it. So that's 6 months long, full-time on-site. Students are learning to be web developers from awesome people like Parker and several other instructors on his team. And then we help them find jobs afterward, and actually throughout deliver careers curriculum from a careers team of 3. So they're in with them every single week throughout the process, throughout that whole 6 months, and even heavier toward the end, of course, in helping them actually applying to jobs toward the end. And then helping them find jobs and get connected to companies. And then on top of that too, we have data science training here. You're in a data science classroom right now. That's why some people are coming in for a stats course. Data science immersive program is what we call it. It's a 3-month-long full-time on-site. And then we also have a 1-year master's program in data science that happens just down that hallway in room 309. And then we also have startup members in the space. 173 the last time I checked, startup members. They're all tech startups specifically, so that everybody in the space is kind of doing similar things and learning similar things, and they can make partnerships, and maybe some of them will hire our graduates, which they've done. That's not the purpose, though. The purpose really is just to have an awesome space with hundreds, actually up to 800. If everybody were here every day, there'd be like 800 people in the space. I think it's usually more like 6 something, or even up to 7, of awesome people learning, pushing themselves, growing in similar ways. So that's about the space, and that's about what we have to offer. And Parker Lewis is a great guy. He's about to travel to Copenhagen, so he might be a little checked out tonight. But hopefully not too much, and hopefully he'll deliver a great workshop for you, and I'm sure he will. Hopefully we'll be doing more of these moving forward too, if Parker keeps agreeing, and if I keep providing snacks, I think Parker will keep teaching me. So yeah, keep coming back. I think the hope is to have something like this every single month. So hope to see you out there. Awesome. Thank you, folks.
Thank you, Parker. Andrew. Hello. I am Parker Lewis. I teach in the web development program. If you have questions about that after, go ahead and ask me if you have any questions at all after. So kind of what we're going to do is, it's like 6:25 right now, okay? And I think it said it's going to end at 8. So I'm going to go for like an hour, just talking about recursion. Hopefully that's why you came here. And so these are the 2 general topics: what the call stack is, and then how to create stack diagrams to help you think about recursion. This is up here because associated with the talk is a GitHub repo that you can clone, fork and clone. And there are some exercises in there. We're going to go over one of them, which is factorial, a very common mathematical case for recursion. And then there are 3 others in there as well. They have short readmes, how to think about approaching that problem, the distinctions between the types of recursion that you're doing. It's all just recursion, but can help to think of the type of problem you're solving with recursion, and that helps guide how you go about it. So that is that repo. It's got 4 modules in there. I think if you can solve those, you can solve most recursive algorithms, all beginner to intermediate recursive algorithms. So what we won't talk about are things like recursion on trees, or recursion on graphs, which is like where recursion really shines. I gave a talk, this last talk that I gave was binary search trees. Was anyone there? You guys there? Yeah, you were there. Anyone else? You were there? Yes. So you guys know we kind of hit this point where it was like, okay, now do recursion. And then I was like, oh shoot, not everyone just gets recursion. So that's why we're here tonight. Right? And so hopefully what I'll do, I'm planning to do either this talk again or that talk again. And then we can do some recursion on some binary search trees. It's going to be awesome, trust me. Sorry, I geek out about this stuff. So let me tell you a little bit more about my history. So I started at Galvanize as a student 2 years ago, 2.5 years ago now. Went through it was called G School, if anyone remembers from, or was like looking at things 2 years ago. It was called G School. And so it was a full stack web development program, and we didn't really have computer science. So I went through it. They brought me back as an associate instructor. I'm a gradable instructor or full instructor. But we didn't really have computer science back then. Then we got some new staff in that was like, yes, we need computer science, and we found out, and I think you know, if you're trying to pass some technical interviews for really whatever field in software you want to do, you're going to need to know some computer science. So what was really cool about my job was that I got to just learn it. Right? Galvanize is a great place. Learn and grow courageously is one of our staples. What are they called? The core values. And so yeah, I was just like, yeah, I want to learn some computer science, and that's what I did. And so that's what I'm hoping to share in these talks. Is kind of somebody, hopefully, or I'm imagining kind of like you, where you want to do well on these technical interviews, you want to do well at computer science, but you don't have any background in computer science. So that's really where I come from too. I mean, I did like a small amount of coding in high school and right before high school, just like programming Legos to do cool robotics things, like a ton of fun, but not, you have an if and a for loop, that's all you have in that type of stuff, maybe some functions, maybe. So hopefully I'm at a similar, or I was at a similar place where you're at, where you're like, great, let's do some computer science, where do I start? So that's what all of these talks will be about. Recursion is a great place to jump in because you can use recursion in a lot of applications, or apply to many, many things, and we'll go over a couple of them today. Can I get a sense of the room? Who was like a boot camp grad or went through a similar program to what Galvanize has? Okay, not as many as last time, okay. Why are you other people here? What's up with you guys? Anyone want to shout out?
Just learning.
Just learning? Just interested in learning? Awesome. Cool. What's your name? Richard?
Yeah, just want to brush up,
Cool.
make sure I hit all the points I need to hit.
Awesome. Okay. Yeah, that's great. I don't really care why you're here. I'm happy to have you. But yeah, just there were like a ton of like boot camp people last time, which was cool. But yeah, so the language. To be honest, I don't even know if I'm gonna open my computer. Like, you might have come here like hoping I would show you how to do the algorithms. I'm really not. Like, there are solutions to all of them in this repo. You can straight up copy them. I don't care. It's open source. But put in a license to make it open source. I really don't care. But what really started making, when recursion really started making sense to me was when I learned about this thingy over here, the call stack. And we'll talk about what the call stack is. But specifically, when somebody showed me the beginnings of how to draw the call stack and how to understand how we can use those drawings. So when I taught this to our students, I was telling them, to me what I'm doing right now is kind of teaching you multiplication, right? So, or how to multiply, right? So, you did multiplication, it was like 19 times 12, right? And your teacher was just like, maybe you didn't learn this way, this is how I learned, right? Your teacher was just like, okay, do these numbers, right? So that's 18, and then, and then it was like, well, what do I do when I run out of numbers? And then they were like, oh, put the 1 up there, right? And 2 times 1 plus that, and blah, blah, blah. I'm not gonna finish it. Okay. But this is what I kind of feel like I'm teaching you to do, right? And you took math, or you took multiplication, and you went and you did crazy cool things with it. And then you learned algebra, and then you learned calculus, and then you stopped because it got hard, I don't know. That's why I stopped. Right? And you took this simple thing, you eventually put it into your mind so that you didn't necessarily have to do it anymore. I remember at one point I could do two digits multiplied by 2 digits, and I was like, all right, cool, like I really understand multiplication. You know, I was like, I don't know, 12 or whatever, and I thought it was really cool, right? So that's really what I'm hoping you'll see it as, see what we're doing today as, is I'm going to show you, like I said, like I'm not really going to touch my laptop all that much. I'm going to draw out stack diagrams and tell you how to think about recursion in regards to or the stack in regards to recursion. And then you eventually, like I'll encourage you throughout to like every time you do recursion, draw a stack diagram, literally every time. So like I've been doing like specifically, I remember when I like did a big project on recursion, that was like, maybe like 6 or 8 months ago, and that was when I really started like really doing these stack diagrams. And like just now I'm starting, like I can go like, that can be solved recursively, and I think I can do it all in my head. But it's really hard, as you hopefully know, and that's why you're here, is like, it's not very intuitive at first. It like, and I say somewhere in the repo, like people learn iteration first, right? For loops, while loops. And that's really more straightforward to a lot of people, and that's why they just choose to do solutions to things that way. But hopefully what you'll see eventually, either tonight or as you do more and more recursion, this is actually, if not more intuitive, which I think it eventually will be, it's a more elegant way to solve problems and yeah, solve problems. So, let's get started. All right. Who knows what a call stack is? Okay, you shook your hand, so you have to answer.
Oh, no, don't pick on me. I only partially know.
What is the part you know?
So what I imagine a call stack is you have sort of an order in which sort of functions or operations are used. So that's a stack. That's all.
Yes, has to do with function calls. That's the one main thing I wanted to extract out of that. Yes, it has to do with, yeah, kind of the order that your function calls are being, not so much called, but the order in which they are run, and then the order in which they return. Can anyone tell me about the call? Yeah?
Is it part of a context, like in something context that gets created?
It has to do with the context
When you
and
call
the scope.
functions,
Yeah,
they get stacked up.
yeah, exactly.
What do you call it context?
Call it the context. There's a context and there's a scope. I don't need to be patronizing. You call it the context. I don't mind. I'm not going to go into. Well, I'll talk about it now. So my stack diagrams shave away a lot of things for you. Let me come back to that point. That will be revisited. So we have this order of function calls and their returning order. What's up with this stack? That kind of is the call part, right? Calling functions. What's up with the stack part? Can anyone tell me what a stack is in regards to computer science? All right, you put your hand up.
Memory queue, more like a stacks one on top of the other.
Right, so what did you say about a queue?
Memory queue.
Okay, so it's distinctly not a queue, and just that word. It's a similar concept. So there are things called data structures, right? Ways that we manipulate the memory in our computer. And so what we can do is we can make, often you talk about them together, stacks and queues. And a queue, if you think, I think like British English uses the word queue to describe like the line at a restaurant or something. So that's the exact image you want to have in your head. Is a queue, you put things into it, and when you ask for them out, they just come out in the order that they went in. So it's like, I don't want to draw a queue because I want to talk about stacks. So stacks are the opposite of that. Stacks.
How about last in, first out?
Yeah, that's what we'll talk about. So stacks again are the opposite of that, which are last in, first out. Sometimes it's called LIFO. So what happens with the stack is I say right here, all right, there are lots of different ways to draw stacks. There's a reason why I'm kind of going to do it this way. So I say, hey, bag of data called a stack. Hold on to the number 8 for me. He goes, okay, I'll hold on to the number 8 for you. He puts it in a little capsule, puts it into the bag that is the stack. And I say, okay, put in the number 12 and the number 13. And then all I'm allowed to do with this data structure is say, pop. Is say, give me something back. It's not like an array where I'm allowed to go, give me the thing at index 6. All I can say is, give me back whatever you're going to give me back. Okay? And so you say pop, you say stack.pop, like that, right? And so that is going to take out the top thing, the last thing you put on the stack, and then give it to you wherever you asked for it. You asked for the last thing, and it gave you 13. And it was important why you wanted the last thing. Now why that's important, I don't know, that's a little harder of a discussion. That's very application specific or implementation specific, but this is what a stack is. And it'll be helpful to see the things coming off the stack. And knowing that the last thing on, or for us, the last function we called is the first thing that's going to come off. Okay, so now we have stacks. So let's talk about the call stack. And what I was going to say earlier is my stack frames are not going to have every single little thing that the actual stack frame of your given language will have. There's more to it. So what I do with this, and I mentioned it again in the repo as well, and I just think it's helpful for people not coming from computer science. It's a helpful way to do things. A lot of times people from computer science backgrounds jam in everything. They just get like all the nitty-gritty things in there, and it's really confusing to tease out what is recursion and what is the necessary recursion, maybe is a better way to say it, and then what's like the other stuff that like, yeah, adds to the solution, but really distracts from the recursion. So what I do is we're gonna, the ones we implement today are gonna be actually exactly like they should be. In the repo, I implement reduce and map. If you know those from JavaScript, many languages have reduce and map, and they can be implemented recursively. And so, but I don't do all of the features that those real functions can do. Like you can have an initial value for reduce, and you can, and yeah, there are things that it does. I strip those away, and same thing. That's the same thing I'm going to do with the stack diagrams. Is we're only going to care about in our stack diagrams the variables and the function calls from our given algorithm or function. That's all we're going to care about. There are other nitty-gritty details of what a stack really is doing under the hood that, yes, they're important, and possibly even to optimize, we might consider eventually, but that's not what this talk is for, right? It's for, let's just understand recursion and maybe start to use it a little bit. And so that's what's going to happen with our stack diagrams. So let's get going with those. All right. We're going to actually start with the stack diagram. We're going to talk about factorials. Anybody want to tell me what a factorial is?
Essentially, one integer multiplied by all previous integers that are less than besides 0.
Exactly. So you may have seen them in math at one point. So it would be like 6 factorial. And factorial is an exclamation point when you're doing math by hand. So that says, that's read 6 factorial. And 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1. It's like, great, 6 times 5. Okay, should be simple enough. But has anybody ever tried to do factorial as a recursive algorithm? What about Fibonacci? A lot more people tried Fibonacci. Yeah, that's why I didn't do it. There's this guy, shoot, his name's escaping me. He's this Google engineer that does these YouTube videos. He's kind of like a wacky guy. You know what I'm talking about? He's cool. He's a JavaScript whiz and like worked for Google and YouTube or something like that. And he has this video. He's just like so pissed that people learn recursion by Fibonacci. And it's like the most common way to learn recursion. And even I'm doing it, right? I'm doing what I call a mathematical type recursion. And it may not be helpful for you at all. Like this part might confuse you more than the second one that we'll go over, which is for each. But it's a good theoretical place to start, and it has very few function calls, and it has very few variables to keep track of. So I think it's a really good place to start when we're trying to learn how to do the multiplication kind of thing, right? You would start with like 8 times 2 before you learn something like 16 times 124, right? You would learn this before you learned that. So that's kind of what I'm doing here with the factorial, right? Is let's strip away more confusing topics like, oh, having to add the number up here and stuff like that, and just look at some really simple things. Why can we solve this recursively? The reason we can solve it recursively is that you can do the same thing on a given number a bunch of times until one time when there's only like one way to do it. That's the most jargony way I could say it. And hopefully that maybe resonated a little bit with some of you. I think it's easier sometimes to understand some jargon, not so specific language. So you do the same thing on something that you don't really know what the answer is until you get to a place where you do know the answer. And that, therefore, helps you get all of the other answers. That's recursion in like the most non-technical way I can describe it. Now let's jump in a little more. So those things I talked about are 2 important parts of recursion. The recursive step and the base case. Probably if you've done any recursion, you've heard somebody talk about a recursive step and a base case. So that's great. And then people are like, all right, so just figure out the base case, right? That's usually where they leave you off. So I'll try to hopefully help you identify where base cases come from. And it's, once you have that, and you have a stack diagram, like you're good. Like you'll pick it up no problem. But that's often the hard part, right? It's like you're starting from the very end. And that's why it's backwards for a lot of people. You're like, what are you talking about? I need to know where it stops. How do I even get it started? So what I think of for a base case is often like, when is something 0 or empty? That can be really helpful. When is something no longer there? I have nothing else to work with. So we'll do it, 1 for numbers in factorial, and then we'll do it here in for each. We'll do it with the size of an array. You keep doing something on the things in the array until there's nothing left in the array. Simple enough, right? Then once you're done, you're all done. So let's do it for factorial. Factorial is 6 times 5 times 4 times 3 times 2 times 1. How we could write this is also n times n minus 1, n minus 2, times, and I can keep going. But I really want to stop there. This is really the most important one. And actually, let me write it this way. Now, a mathematical formula, mathematical definition. And this is true, right? N factorial equals that. I mean, I can't do like mathematical proof for you, but I can just say that's the answer, right? That is just a mathematical fact, that n factorial equals n times n minus 1 factorial. Great. Okay. Well, that doesn't really help me, Parker, because what if n is 6, and then I just keep doing, or let me do a different number just because, right? N is 4. Now, 4 factorial equals 4 minus 1 factorial. Okay, so that's 3 factorial equals 3 times 3 minus 1 factorial. Stay with me. That's 1 factorial equals, okay, here we go. Now things are getting interesting. 0, oh, sorry. That's the answer. 1 minus 1 factorial. Uh-oh. 0 factorial, what does that equal? It's 0, times, what? 0 minus 1 factorial. Okay, so negative 1 factorial. And negative 1, sorry. Negative 1 minus 1 factorial. Okay, this is weird, because this one's going to equal 0. This one is going to equal a negative number. This is going to be 1 times negative 1. So how did my factorial start getting negative? It eventually doesn't make sense. So what you just have to do, and again, I don't know the mathematical reasons of how this doesn't break the universe, but eventually, I don't know, maybe some mathematician just decided, or I don't know, they did something. They just said, let's just say, somebody just said, no, stop. 0 factorial is 1. It's just the way it is. Now, in math, like, that's why I stopped liking math, right? It was like, man, people just kind of started making stuff up. I don't really get why. Like, that's no fun. People just get to make up rules and then I have to follow them and try to get an A. Like, that's stupid. Okay? What's kind of cool, I don't know, maybe I just grew up a little bit or something. Like, what's cool about this is, and especially with programming, is you get to do that. That's why people, I think, a lot of times like programming, is that you get to make your own world, right? You get to decide the rules of your own world. So, what we will do is, this one we're basically just going to copy. Like, they give us this fact, and we just base our recursion off of that fact. What you eventually get to do with recursion, and hopefully you see it as an opportunity and a fun thing, is that you get to decide when things stop. When there are givens in the world, you get to decide the given. You get to decide that you stop recursing when there is nothing left in the array to recurse over. That's when you stop. And you get to decide that. Based on that decision, great things happen for you. And you just have to be able to take advantage of them. And we'll talk about how to do that. So this is my case for a base case. Sometimes it's just given to you. And that's most often with mathematical formulas. And so they're a good place to start, but then you get to make them. And you get to decide them. They're often very similar, right? Like things equal 0, or things are empty, things like that. And so you find patterns like that, but it's cool. You get to decide that. And so we'll do that with for each. Let's finish up with factorial though. So we know that 0 factorial is 1. Based on that, right, this becomes 1. So this equals 1, which means this equals 1, which means this equals 2, which means this equals 2, means this equals 6, means this equals 6, means this equals 24. And then we got the answer to our question. Because we had somewhere to stop. We had somewhere to say, this is the way it is. And there's no ifs, ands, or buts about it. Now, how do we see this in code? Yes?
So basically nothing gets returned until you hit your base case, and then the return propagates there on out. Kind of like nested dolls where you don't get the outside component until you've assembled the inside components.
Yeah, I don't usually like to use the dolls analogy. A lot of people do. Are they called Russian something dolls? I'm not sure. But you know, where the smaller one is inside the smaller one. People describe it sometimes. I won't use that because to me stacks help. Like that can be like this really weird meta abstraction weirdness to me. But yes, you eventually get down to that place and then you can start building back up. And to say that you don't return anything until you hit the base case isn't technically true. You can call other functions and those can return and do stuff. But your recursive function, yes. Once you hit your base case, then magic really starts to happen. Okay. So okay, so here is the algorithm. I'll do it in JavaScript-y stuff. Function, factorial, equal, I can write JavaScript. And so we'll just call this num. And actually, I don't need anywhere near that much space. So this one, I'm just going to give you the algorithm, which is, right, I need to put in a base case. Like the first thing, if you can get that base case, you're going to be 90% of the way there, most often. Maybe like 80% of the way there, most often. Now that's not always feasible, and so you can still work without necessarily knowing the base case. It's just easier if you do. So I usually will even sometimes just guess at a base case. Like it's so powerful to have it that even just guessing, maybe I guessed wrong and I need to adjust my base case, but just having somewhere to start. If you're having trouble starting your recursion, just pick a base case for yourself. Try to think of something in the world that you're living in that bottoms out, that is like 0 or none, or you're done somehow, and just go from there. But we know our base case, which is this, which is if n equals, num equals 0, return 1. Now, again, so that part hopefully is easy enough to see. Now the recursive step might be a little weird, especially in code. I mean, the recursive step here is, okay, just multiply it by the thing that came before it, like someone else said. Okay, so let's try to just kind of put that into code for as much as it's worth. Multiply it being num, times the thing that came before it. Yeah, so here I'll kind of, the thing that came before it times all the things that came before that. How do we do that? Oh, well that, okay, sorry, I wanted to make that really nice, but that is that. That line is equivalent to this line, more specifically this part. Multiply it by the thing that, damn it. Multiply it by all of the things that came before it. Okay, so if you couldn't have gotten there by yourself, that's okay. Maybe what you would have done, I'm going to erase all this. Maybe what you would have done, probably not because I haven't taught you it yet, but eventually in the future, hopefully what you'll do is start thinking in terms of function calls. So this is how a stack diagram works. I'll break it down. So this I don't always write off to the side, and actually I'm just going to write fact instead of factorial, just for quickness. Check this out. So, fact of, yeah, we can do 4. And then that's that function. So, when you call a function, it puts it on this thing called the stack, the call stack. And all that is a stack that has all of the information about a given function call. Now, you don't even really have to understand that much about what a stack is to be able to use the stack diagram. That's why I think it's so useful. Like, and what's really cool is eventually you really do understand stacks by doing this. So if you don't understand what a stack is, don't like fret. Just try to get the stack diagram because they're easy enough. They always go up and then they start coming down. So what I do inside of stack diagrams, if you had paper, it would be great. I realized I should have like wrote, hey, bring some paper. But there will also be a video online, so you can do that. So what I do is I write down all of the variables, all of the parameters, all of that. Again, I'm going to use fact and why don't I just do it? Okay, now it's the same. So factorial, fact of, and equals 4. And then literally what I do, often this is in pseudocode when it's more complex. I'll have a little bit of pseudocode written out, right? Like, okay, I think this is my base case type of thing. And then I literally run through, line by line, what's going on inside the function. So I'll just start back up with the function. Literally, like, I have this on a piece of paper, I write the function right here, and this is what I do. Okay, run the function. All right. Does n equal 0? Nope. Okay, move to the next thing. Bam. Another key part of stack diagrams, so we'll put it in another color, is the return. So that's a really key part that you want to keep track of. In this case, that's the end, and we already know that, right? We can just see it. But that might not always be the case when you're doing recursion, other recursive algorithms. You may call the recursion and then do some more things. So it's important to remember where you are when you return, when you do any of these things. Okay? So a return is a really key part. Then we can just see that it's 4, so that's cool, easy enough, times of 4 minus 1. Cool. Again, this might not mean much to you right now, but watch how it goes. So, as soon as I see another function call, right, another invocation, another parentheses, boom, that means I need another stack frame. I need to set up my stack frame with the right arguments. So this one is 3. I know that that equals 3. I can just do that. All right, I'm all set up. Now let me run my function. Is it 0? No? Okay. We're going to return factorial of, return n times n minus 1. N times factorial of 3 minus 1. So I'm going to speed up a little bit at this part because it gets repetitive until we get to the base case, which is perfect. Even what I'll do sometimes is draw an arrow up to this saying, hey, when you're done here, come right back to right here, right where I called the function. Ooh, this is going to be too tall. All right, let me save a little space. All right, so n equals 2. 2 times 2 minus 1. Okay. And then that will take me up to a new stack frame. N equals 1. Sorry, my pen's running out. Turn 1 times factorial of 1 minus 1. Bam. All right, that's 0. All right, top stack frame. Sweet. Here we go. Here's where some magic happens. We're going to see why we like stack diagrams. N equals 0. Right? All those times we ran through this, we did that. So now we're up at this top one. So let's run our function again. Start here. N equals 0. Yes. Return 1. Sweet. So why is that important? Here we go. Return 1, and it says, I do this. A student of mine had another way that I liked, but I like to do this. It's like, okay, back down to here. Because I would like cross it out, and I was like, that's not right. It's like, it works. So, now I put 1 there. And it came back exactly where the function left off. Now 1 times 1, I don't know, I can write it there, I guess. So here it is. That's what we're returning. Oh, yeah, sorry. 1 times 1 is 1. Thank you. And then we go back down. So we know that this one equals 1. Should, right? Once I do that, these things pop off. Right? This one, return, comes off the stack. Now, this is a 1. This equals 2. And that one, sorry, there's no arrow there. This one comes back down. So now that's 2. Take that off. Now we do this one. So that equals 6. Bring it back down. This equals 6. So this equals 24. And then that's our last stack frame. So what is returned to us, wherever we called this, again, this abstracts a lot of specifics away, because probably down here you had, I don't know, you had a variable somewhere in memory storing this variable. So now we see we return the final thing, it's done, right? There's nothing else to do, and we got our answer. Hopefully a little bit of the magic is demystified. Yep.
Yeah, I remember the term I was looking for, it's execution context.
Execution context, yeah. So that is wrapped up in here. Inside of here is scope and execution context, but I'm just gonna say don't worry about it, because you can get into nitty-gritties about that. This is a more high level of all of that. Execution context takes into account these variables, things like that, the function calls themselves, the lines, specific lines of the function calls. It holds a lot of stuff like that. Trying to simplify it as much as possible. Because, as you see, even though we simplified, we still got the right answer. Only the relevant things were in the stack diagram. Okay. So, great. I want to talk for about 30 more minutes. I don't even know if we'll go that long. But, hopefully that was helpful. Get a rough idea. This time we had the idea. So next time we'll get a rough idea. But get a rough idea. This will be more pseudocode next time. Get a rough idea, especially of your base case. And whatever else it's supposed to do, and the recursive step somewhere. And then draw it out. Now I got it right the first time, and I'll get it right the first time in front of you for the next time. But you won't always get it right, which is great. Which is perfect. It strengthens your understanding of recursion so much better when you get it wrong. It's great. I know I'm a teacher, and so yeah, I say that stuff, and maybe you're like, oh, teachers always say that stuff. It's so much better to get things wrong. So, try this out. I hope you'll try it out. I hope you'll try it out on those functions. Let's talk about for each. I want to stop and ask any questions, anything I can clarify.
What if in the first place you got a negative n for some reason?
Okay, so that's another thing about the repo, and in general, when I'm teaching computer science things, there are lots of things that could break this. Like, what if you pass in an array? What if, lots of things like that? Yeah, we're doing happy path here. We're just saying you're always going to be past the right thing. If you had to take into account those things, yeah, you just have like a lot more boilerplate up here of like if n is not, or if type of n does not equal number, return you're stupid, or, like there would be other cases that you could handle. I'm not saying you're stupid. The caller of the function is stupid. Right, you can have all that. This is, and I'm pretty sure I explicitly put it in there. Like these are very happy path. Things will go right in that respect. People will, to speak more technically, like use your interface correctly. Of course, that's not always true, but you can act as if it is just for the learning part of it, right? If we had to take into account all that, we'd have a bunch more checks to be annoying. So these are very sliced, everything's sliced away as much as possible to just focus on things. Other questions? Let's do for each. Can anyone tell me what for each does? Some languages don't have for each, they just have beefed up for loops, but if you're familiar with JavaScript, especially for each, anyone? And yeah, that's basically all for each does. For each, yeah, just takes everything, right? And does the thing that the callback in it says it will do. Yeah. So here I can write out a for each. I'll write it over here because it's kind of gross. That sucks. All right. So if we have something like, all right. Again, I'm gonna keep it super simple. A, B, C, D. Each, do an arrow function. Whatever, I'll write it all the way out. Yep. So, all for each does is on every single one of these, for each of these, it will call this callback function on that element, right? So it passes, this is where it gets a little tricky for people when you have to call a function inside of a recursive function. So we'll slow down when we get there. But all it does, really high level, is all it does is it takes every number, every value in an array and calls the callback function on that element. What you do inside that callback function does not matter. It's just a callback function. It's just a function. So that's what for each is going to do for us. How do we do that recursively? So based on what I've said a couple times, who can tell me what our base case should be? Before we write out anything. That's always what you want to be thinking. Yeah?
The list is empty.
When the list is empty, when the array ends, do you know JavaScript? Python? That's why you said list.
Sorry.
No, that's perfect. So how do you determine that a list is empty in any language? What's a really easy way to do that? Go back to it. You can check the length, right? If the length of something is 0, if the length of an array or a list or whatever you call it in your language is 0, it's empty. There's no ifs, ands, or buts about it. So that's our base case. And it was one of those patterns I told you about, right? Something is empty, something is 0. Those are the same in this case. An empty list is a list with 0 length of 0. So now we are going to do it slightly differently. We are going to write, let me write my function over here. So we'll call it function. And it will take, what do I call it? For each. It's going to take an array and a callback. It's going to take two things. It's slightly different than this because this is attached to the prototype. You know how JavaScript works. So ours will be maybe more of a traditional function where we will just say for each inside of, I'm just going to do numbers because it's faster. Now, call this function. This is what ours will look like. This is what native JavaScript will look like. Sometimes it's really helpful to have these things too. While you're working on them, if you get stuck, at any one given place, just try to write something else. It just keeps your mind going. Just try things. They could be completely wrong, but it'll help. So, again, let's write our base case. If array.length equals 0. Now, what I'm going to do on this one is just hold off. Because, I know what my base case is, and that's one and a very important step. But what I do when I hit my base case is also not always very apparent. And it's different for different cases. So I'll just kind of leave it empty for now. We'll fill it in later, don't worry. What do we want to do otherwise? What's something we know we need to do? in order to make this happen?
Pass in value.
Pass in a value to what? Get an element out of their array. That's one thing. What do we do with that value out of the array? What does regular for each do with each element? Passes it to the callback. Takes an element, passes it to the callback. That's what our function needs to do. Now, that's not the same as the recursive step, which is I think where people get confused sometimes when you have to call a callback on things. Calling the callback is what your function's doing. Recursing would be what?
The function calling itself.
Function calling itself, but what would be different this time about than when we called it before?
Then you would need to pass something in within that function. So for instance, if you're doing the factorial, then you would implement your factorial at that point in the function call.
You would, and notice what we did with factorial. It's gone now. We did it, it's slightly different here, but I'll hopefully translate it. Which is, we did factorial again, for sure. We did it on a different thing, though, distinctly, right? Because if it was 4 factorial, when we called factorial again inside of our function, we did it 4 times factorial of 3, something different. Specifically, in that number, something smaller. Right? And that's what you want to be doing with recursion, is usually, and I just off the top of my head, I will say always, you're doing it on smaller things. That's why you're doing recursion, is you eventually want to hit the base case. So what is doing it on a smaller thing in for each? What is the thing that we're calling it on?
N-1.
That's in factorial.
Sorry.
Somebody said it over here. The array.
The array.
But not just the array, a smaller version of the array. So let's kind of that was a lot of words, let's talk about it. Right? So I'll make this pretty verbose. So let's say var, let or whatever, curval. That one, let me just tell you, but you may have been able to get to it yourself. You don't have to do this necessarily, it's just easier to conceive of. Will be array at 0. That's our curval. Then we needed to pass it to the function. I'm not sure who said it, but pass it to the function. Well, that function is called CB, and we'll pass it curval. What CB does in this particular case doesn't really matter to us. We don't really care, because it's just all for each says is just do it. Just do whatever that callback says. So just do it. Thank you. Okay. Just call the function on the current value. Now, all right. Yeah, I'll just say it. I don't know why I wouldn't. I'm gonna do it wrong real quick, and then the stack diagram will show us what's wrong about it. I'm not doing it wrong. I'm leaving something out. Let's put it that way. I'm leaving something out. So then I'm going to do the recursive part, right? For each on, I'll write it, I want to do it on a smaller part of the array. How would I do that in any language? It's called the same thing in all languages. Slice it. You slice the array. Right? And slice, you can do a lot with slice, but you can basically say start from here and go to there and just give me that part of the array. So what we'll do is say start from index 1, go to the end of the array, and just call it on that part. Let me give myself a little more room. So I'll do that. I'll call this shortened array equals, I'll just write it and then move. So you can check it out on your console or in Node or something later what this does. But I'll show you what it does. If my array is 1, 2, 3, 4, called an array, and I do new array equals r dot slice of 1. What it will do is new array will equal 2, 3, 4. It started from index 1 and gave me the rest of everything. For more parameters you can pass in, you can use slice differently. Different languages implement it differently, but every language can do this. Gives you a new array, that's important. Not for our purposes necessarily right now, but often it's important. Gives you a new array with less value, or with the sliced out values. So now we have shortened array. Now we're going to call for each on shortened array, and we're going to pass in the same callback. Let's call that good. That's enough pseudocode. I wrote it out very explicitly. You could have just written some pseudocode if you wanted, but this really helps. So let's do some stack diagrams for this. Notice, what's one thing that's really missing from this? Can anyone spot it? What this is really lacking, this function? Can you say it louder? Return. We're not returning anything. Returning is really important in recursion, and we're not doing it. Now that's fine, and I did it intentionally so that we can see where in the stack diagram that becomes really important. So let's check it out. I'm going to do it on, we'll do that one. Yeah, we'll do this one, but I only want to do it on 3 things. It's just faster. So that's the function that we're running. That is going to be, I'll just write it again. And this time we'll do an error function. That says console.log L. It's the same thing as over there. It's just in one line. So that's what's happening here, and will be happening all the way up. I'm just not going to write it long. So let's do the same thing again. So this is a part to literally, I'm teaching you how to multiply. It's a step-by-step little process that just becomes ingrained in you, and then you get really good at it. So that's why I don't have any notes. I've just done it a gazillion times. It just becomes ingrained. So what am I going to do? I'm going to set up what's happening inside of here. So R equals 1, 2, 3. I'm not going to write the callback one because it's always the same. So callback equals callback. It's just CB. It's always CB. All right, so we check here. Is the length 0? Definitely not. Let's go here. All right, so let me write curval. Curval equals 1. Easy enough. CB of curval. I'll write this all the way out one time, and then I'm going to go over it faster. But it is important because it uses the stack a lot and actually addresses something I think she said over there about calling functions inside of functions. So watch. Now I call CB on curval 1. Same thing needs to happen. As soon as that function gets called, boom, new stack diagram. Up to here. What does that function do? Oh, it's bigger over here. So all that does is it takes its first element, and that equals 1, and then it console logs it. So what does that do? That actually puts another thing on the stack, and that's magic. That's just how JavaScript works. It knows how to print to your console, right? It does that, puts it in your console. I don't know, this will be our console. Prints the number 1, comes off. Okay, do I have anything else? No. Technically that returns undefined. You can go all the way down here. This is technically undefined, but we're not storing it. We're not doing anything with it, so it doesn't really matter. And that comes off. So if you notice, we've already actually done some really good work. We've done the first thing we were supposed to do. We made it print to the screen. It's really simple, right? It would definitely be more complex if this were a harder algorithm, but we did good work. Basically, we're on the right track, right? I followed it through, and I'm like, okay, I think I'm doing well. Well, let's do this one. Shortened array equals array.slice1. So, shortened array equals r.slice of 1. So this is another built-in, so I'm kind of going to go over it quickly, right? Because I don't actually know the internals of JavaScript. But what I do know is that this is what it's going to return. Magic JavaScript doing its work for you, because it's a built-in function. Comes back here, so now this is 2 and 3. If I'm honest, no, I don't draw these every time. If it's a built-in function and I know what it gives out, I don't draw it. I might encourage you the first couple times you do it to literally do it so that you remember this is what the stack actually does. But I won't do it the rest of the times, just so you know. Those things really do go on the stack each time and really do pop off every time. And that's why your function doesn't continue, because there are things above it. But okay, so we come back to here. Now we're doing something, right? Oh, that's funny. For each of 2, 3, and callback. Awesome. All right, new stack frame, right? Basically this thing again, but on 2, 3. All right, I'll go a little faster this time so we can get to some interesting base case stuff. Array 2, 3. Curve val, I should point over here actually. Oh, so we look here, not equal to 0, good. Curve val equals 2. CB on 2. So again, put stack frame, pop off. When it pops off, it has done that, it is printed. And then this one is good to go. So we're done with that one. Shortened array equals the slice, here, I'll write it. Son does its slicing, comes back. Now we're at 3. Make this short. Now we do the for each on 3, and we pass a callback, just like we did here. That takes us up to here. All right, starting to get interesting. Maybe not yet. R equals 3. I'm going to go really fast on this one. Curve val equals 3. CB of 3 on, comes off. That's over there. Shorten array equals an empty array. Here we go. For each on CB. All right. Array equals this. So now we've reached where we kind of wanted to be. We told ourselves, hey, we want to be where something is empty. We see it visually now, which is great. Now, what do we do? What's something? Anybody know what we should do now? Like, great, we reached our base case. Maybe take a look at the terminal or the console.
Are you ready to display your output once it's empty?
My output has already been displayed.
Or your final answer?
But wait, what?
Your final answer.
But what was our final answer? That's kind of the interesting thing about recursion, is that you were expecting an answer. What was the answer in this case? Just printing out the thing. There wasn't actually any answer to be had, right? Before, the answer was we wanted 24. It doesn't always have to be that way. Again, I'll plug my thing because I worked hard on it. There are different recursive archetypes, like things that you tried to do with recursion. This one really didn't matter what the answer was. That's what for each is for. Like, you don't actually ever do something. Now, if we were doing something really similar, but we wanted an answer type thing, we would be doing like map or reduce, both of which are in the repo. There are some subtle, they're not really even that different. You just have to care more about the return value. But if we look at this, how are we ever going to finish this stack frame? What's the way you finish a stack frame? How does a stack frame pop off? Return. Yes, people are saying it. You return. Okay? That's how a stack frame pops off, and the return value goes back down, and then you're in the next stack frame. So, yeah.
Parker, if there's a mistake in one of the stacks, that's where you have an error. The stack stops and it's frozen, so you can look at the call stack to debug the error. Is that the realm we're in here?
That's, yeah, you mean like in your terminal when it throws an error and then it shows you the call stack?
Right, can I go into Chrome DevTools or something? And look at the stack?
Yeah, you can do that in Chrome DevTools, yeah. Yeah, you kind of got to know what you're doing with Chrome DevTools, but yes, you could. I don't know if you can do it to where like show me the call stack when an error happens, but you can throw a debugger. If you're familiar with the Chrome DevTools, you can throw a debugger and it will actually, yeah, there's a little tab over on the side that shows the call stack step for step. Basically this. I didn't make it up. It's in the Chrome DevTools, right? It's basically this. It shows you all the variables. It shows you what line you called things on. Exact same thing. And you can use a debugger to stop yourself, the word debugger, inside of there. Also, what I kind of thought he was talking about was, right, when there's an error, you see all those freaking lines. That's the call stack, if you didn't know.
Yeah.
It's usually file paths and maybe even line numbers. Depends on the language too. But that's the call stack. And so you can actually look at that sometimes when things break and go, oh, it went 6 times, but then once the array was, it went 1 too many times. The array was 0. Oh, I must have not accounted for something somewhere. You can look at it that way too. It's kind of hard, and especially if it's a really like long-running algorithm, there are lots of things on the call stack. That's why I like doing this, right? Keep the things short, and you can see them all.
Yeah, and I think that a big problem is when you're processing anonymous functions, they're harder to debug.
That can be true, yeah. Because, yeah, the call stack isn't as informative then. Yeah, that's true. So that can be another thing, like, so this is an anonymous function. If I would have just written, like, foo right here, in the call stack it would show up as actually foo. In the DevTools, it does just say, like, anonymous. It might even be in parentheses, I'm not sure. It'll say anonymous was called. Okay, so back to here. So we've hit our base case. We just don't know what to do with our base case. Anybody have an idea? It's simpler than you think. Somebody said it over here. Yeah, you just return. That's kind of why I chose this one. That's all you do. You just return. Okay? And now, okay, so I hit here, oh, return. Okay, doesn't matter. Really, we weren't storing this value. That's not what for each is good for. It's what map and reduce are good for. But we're not really storing the value. Okay, so back down here. Now, to be explicit, we should have done something better here. This will actually continue to work because that's just how JavaScript works. But what would be better if we had in here? Yeah, you can either return this or you could just return. Regardless, even if you don't have it, it will return by itself. It's just how it works, right? So, I don't know, you could put it explicitly. In this case, you don't really need to. But to be explicit about it, now we return, right? And that's what lets us know, okay, boom, that one's done. All right, come back to here. Oh, look at that. Nothing else to do, right? There's nothing left. Return. And return. And then, I don't know, keep doing whatever was below you if there was anything below you. And keep going.
Parker, in each one of those contexts, there's functions going on, there's a variable being assigned, I imagine. Am I right?
Yeah.
Yeah. Anything else basic happening there? Yeah.
I mean, these if statements are happening too. There's not a great way to represent them necessarily. Like you could literally draw them in there. It's just kind of duplication, in my opinion. So yeah, there's like that stuff going on. There are for loops, which is also just assigning variables and changing variables. But yeah, the main things you're looking for are variables and function calls. Oh, and return statements. So I guess 3: variables, function calls, return statements. And as you can see again, okay, it did it. That was our whole job, and that was only our job. A lot of times people make recursion too hard, make it too difficult. That was all we needed to do. We got to a certain place, and we got there, and that was good. All right, questions? Not quite done yet. Oh, I'm almost done. Questions on that one? Okay, so if I could sum up, try to make use of stack diagrams. Try to make use of them specifically on really simple things first. Great place to start are the 4 that I have in that repo. Eventually, there will be walkthroughs even of those. They're not right now. This video is going to go up, and then I'll make those other ones. It'll take you through drawing the stack diagram. But you've seen it, you can watch this video too and kind of see what I do. But again, for those stack diagrams, you're making a stack for any given, or sorry, a stack frame for any given function call. And in that, the reason you're doing that is so that you can track variables and make sure that your variables are lining up. And then you're looking for function calls, which make new stack frames, and return statements, which bring you back down and pop things off. Using those tools, using that tool, I should say, you can solve a lot of problems. Are you going to be able to go out and like traverse a tree right now? Probably not. I'm not saying that. But hopefully on these, beginner to intermediate recursion problems, you can get those down. That, I'm hoping, will build your intuitions about, already the kind of things I said, right? Calling it on smaller and smaller subsets. Slicing is very common. Subtracting is very common, calling things on smaller and smaller subsets. Shoot. For some reason my mind just went blank as to the other thing I was going to say. Oh, looking for your base case to be something 0 or empty. They're important things to kind of extract out of here. So you want to be calling it on smaller subsets, and you want to think of where you're going to end, often being when things are 0 or empty. Tracking all of that in a stack diagram, changing values as necessary. Just get as nitty-gritty as you can. If you really want to get it, like I just have no other way to do it. I have no other way to teach you how to do it. Like none of them are here, so I'll talk crap about them. Some of my students, I was teaching them this, and then they came and asked me questions, and were like, "How do I do this?" I was like, "Show me your stack diagram." And they didn't have one. I was like, "It's the only way I know how to do it." So hopefully it helps. That's where I'm going to stop. I'll ask for any last questions. Yeah.
So, I haven't solved some algorithms with recursion, and what ended up happening is I got this out of memory error because the stack is really bad. Do you have any recommendations on how to overcome that?
Yeah. So what that is happening is you don't have your base case, or you might think you have your base case, but your base case is never being hit. So everybody's heard of Stack Overflow. The website where it gets its name is Recursion. It doesn't have to be Recursion, but it's often Recursion, where you never set a base case. So it just kept putting functions on the stack, function on the stack, on the stack, on the stack, on the stack, and then the stack is only allotted so much memory in the internals of your browser, it only is allowed so much memory. So eventually it just says, hey, okay, I can't do this anymore, and throws that error. So that's what was happening.
Is it possible that the data set is so large?
Yes.
Okay,
That's
that
another
also,
thing too.
yeah.
Yeah,
So-
that happened with one of our exercises.
Right. So in that case, maybe the for loop or just regular.
Yeah, you either need a bigger computer,
Yeah.
better browser, or yeah, that's like your constraints have come to bear, right? And
Yeah.
you need a different solution.
Okay.
Is browser storage about 5 megs?
Ooh, I don't know.
Okay.
I have no idea.
Already asked already. What happened to the rate after the recursion? Does it go away because it's crystallizing it one by one? And does the array still exist and fixes or?
You mean like this array, and then all of the smaller ones?
Yeah, is it gone after?
Yeah, after the stack comes off, it goes away. Garbage
so
collected.
we cannot use it in the later on.
You kind of could because it's a reference type. So as long as you have a reference lower down to the same array, that's why we actually use slice instead of like mutate. Instead of using splice, for instance, splice mutates and gives you back the same array, which is the same memory reference. So in that case, yes, you can use them at different points in the stack, which you really don't want to do. Okay? It breaks a lot of best practices and concepts of computer science, encapsulation being the big one.
So can you give me some real use cases of recursion? Because the thing is, I know it's a very important concept to study. And it's asked a lot in interviews, but I've never really used it in.
So, yeah, so to give you some, right, it would be if you need some more fine-tuned control over things like this, right? You need a little something special for each, so you have to implement it yourself. Why you might use that would be, let's say you get some data, and so I do primarily web development, right? And so, okay, I got this data from an AJAX call. Now I need to make a bunch of these. I need to make a bunch of components or a bunch of HTML elements based on this data. And so, again, if I need some more fine-tuned control, especially in something like web development, where maybe I even need to make other function calls or like other AJAX calls in the middle of that, I might need to really control my recursion. And so that's the thing is, to be honest, no, you don't really need to use it that much. A lot of things do it for you, and you don't even know. You do them more in a theoretical sense, okay? And so another really common use case I said earlier were trees and graphs, right? And when do you do that outside of learning computer science? Now, why it's useful, while you may not implement it yourself, there may be, you're using depth first search when you're using document.get element by ID, one of those, uses a depth first search. Depth first search is going to use recursion. I can't specifically answer your question and think of like why it would be important to know recursion in that instance, but that could be a reason, is that you're like, oh, this is doing it recursively. I don't know, maybe to come back to your point, you're just using too much memory in your browser. That's not likely, your browser has a lot of memory. And that's where that's why they're computer science topics, is now you're getting to the edges of like when you need to optimize, right? If many of you are, just junior level engineers, no, you're not gonna be optimizing a recursive solution, but those people at Google that make it super quick to do a Google search, they had to think about some of these things. And so that's why some people, like a lot of programs, don't necessarily teach computer science because it's not super practical. You don't do it every day. One, interviews, right? Maybe why you're here today, because it was in the title to crack your interviews. And yeah, it's, same thing with, I got a similar question with binary search trees last time. You don't, right? Your day to day, the only reason I do it is because I teach it and I want them to learn it. But, in a real, out there in the wild, you're going to use things that use recursion. Whether you implement the recursion, not very often. Yeah, so not a very satisfying answer, I know. You use it when you're doing computer science. But cool nonetheless. All right. Hopefully. Did you still have a question in the back? Okay. until like 8, unless nobody's asking me questions. Then I'm gonna go home. But yeah, thanks for coming.